Hi, this is Sonia Doucette. In this video, I'll show you how to find the Kn value for a neutralization reaction involving a weak acid and a weak base. And in order to find the Kn value for these types of problems, you first need to identify the net ionic equation for the given neutralization reaction. In this specific problem, you're asked to first write the balanced net ionic equation for the neutralization reaction involving equal molar amounts of nitrous acid and ammonia. Then calculate Kn for this neutralization reaction. The first thing you want to do for these types of problems is to identify the acid-base properties of the two substances involved in the neutralization reaction. The first substance we're dealing with here is nitrous acid. You can look up a Ka value, or an acid dissociation constant, for nitrous acid, and at 25 degrees Celsius the Ka is 4.5 times 10 to the negative 4. Any K value in general less than 1 will mean that the acid you're dealing with is a weak acid. So this Ka value is less than 1, and we can say with confidence that nitrous acid is a weak acid. We're also dealing with the substance ammonia. We can look up a Kb value for ammonia in a table of base dissociation constants, and we find when we look it up that we get a value of 1.8 times 10 to the negative 4. Similarly, if Kb is less than 1, then the base is considered a weak base, and this Kb value for ammonia is indeed less than 1. So by identifying the acid-base properties of the two substances involved, we can tell that we have a weak acid and a weak base. So we're dealing with a specific type of neutralization reaction here. Once you know this, you can use the generic form for the net ionic equation for this type of neutralization reaction, which is a weak acid, weak base type. The general form for the net ionic equation is the weak acid plus the weak base, giving you the conjugate acid of the weak base and the conjugate base of the weak acid. To take the specific substances we're dealing with and plug them into this general form, we have nitrous acid as our weak acid, ammonia is our weak base, ammonium is the conjugate acid of that weak base, and the nitrite ion is the conjugate base of our weak acid. So here is the net ionic equation for the neutralization reaction for the specific substances we're dealing with here. Now to find Kn, you need to multiply known equilibrium constants for reactions that add up to the given net ionic equation that we just found. For weak acid, weak base type neutralizations, there are usually 3 reactions with known equilibrium constants that we need to deal with here. The first one is the reaction for proton transfer from the weak acid to water. So that's nitrous acid plus water transferring a proton to water to give the hydronium ion, and then you're left with the conjugate base of the weak acid. And we've already identified the Ka value for that reaction to be 4.5 times 10 to the negative 4. The second reaction we usually deal with for weak acid, weak base neutralization is the reaction for proton transfer from water to the weak base. And the weak base in this case is ammonia. And we're left over with the ammonium cation, which is the conjugate acid of the weak base, once water has transferred a proton to it, and you're left with hydroxide, which is what's left over when water gives up one of its protons. And we've identified the Kb, or the base dissociation constant for this reaction already, to be 1.8 times 10 to the negative 5. The third reaction of interest here is going to be the neutralization between the hydronium ion that comes from the reaction where the weak acid transfers a proton to water, and the hydroxide ion that's left over when water transfers a proton to the weak base. So what you'll get here for the neutralization between the two is hydronium plus hydroxide, giving you 2 waters, which is what is left over when the hydronium ion transfers a proton to the hydroxide ion. And the K value for this reaction is really the inverse of Kw, so 1 over Kw, and that is equal to 1.0 times 10 to the 14th. Now before we can multiply these 3 K values together to give us our Kn value for this net ionic equation and for the neutralization reaction that we're dealing with in this problem, we need to check to make sure that these 3 reactions add up to give the net ionic equation that we've already identified. So what we want to do to figure that out is to get rid of species that appear on both sides of any of these 3 equations. So we can get rid of hydroxide, which appears on both sides. We can get rid of hydronium, which appears on both sides. We can get rid of 2 waters on each side. And when you do that, you're left with nitrous acid and ammonia as the reactants, and ammonium and nitrite as the product, so the conjugates of our weak acid and weak base. Now that we have ensured that adding up these 3 reactions will indeed give us the net ionic equation that we've identified, we know we can use their K values and multiply them together to find the Kn value for this neutralization reaction. So we can say that Kn will be the product of all 3. So it will be Ka times Kb times 1 over Kw. When you substitute in the terms, you get 4.5 times 10 to the negative 4 times 1.8 times 10 to the negative 5 times 1.0 times 10 to the 14. And when you do the math there, you're left with 8.1 times 10 to the 5th. So here is our Kn value for this specific neutralization reaction that we're asked to deal with in this problem.